Hello young number theorists, and welcome back to our part 2 of our first lecture about congruences. We've seen in lecture 1 how to solve number theoretical problems using congruences, in which I used addition and multiplication on a clock without saying one word why these operations are well defined or even make sense. So what does it mean to multiply or to add 2 hours on a clock? We know, for instance, that in a 5 hours clock, 16 points to 11, which points to 1 modulo 5. But we also know that 18 and 13 and 3 point to the same hour modulo 5, which is 3 o'clock. And to make sure that addition works properly on a clock, one must have 16 plus 18 is the same thing as 11 plus 13, which is also the same thing as 1 plus 3. By a straight calculation, we know that 16 plus 18 is congruent to 34 modulo 5, 11 plus 13 is congruent to 24 modulo 5, and 1 plus 3 is obviously congruent to 4 modulo 5. But are all these the same? The answer is yes, because 34 is actually 4 modulo 5, 24 is 4 modulo 5 too, and 4 is of course 4 modulo 5. More generally, we shall prove that if A is congruent to B modulo n and C is congruent to D modulo n, then we must have that A plus C is the same thing as B plus D modulo n. Moreover, why would things work properly for multiplication? Namely, why from here we would have 16 times 18 is the same thing as 11 times 13, which is also 1 times 3 modulo 5. This is actually true, and if you would like to do this systematically, one has to prove that if A is congruent to B modulo n and C is congruent to D modulo n, then A times C is also congruent to B times D modulo n. To prove both of these claims, let us first start by defining what it means that A is congruent to B modulo n mathematically. Indeed, we say that A is congruent to B modulo n when A and B have the same remainder when divided by n. This is actually equivalent to saying that n divides A minus B. So A is congruent to B modulo n if n divides A minus B. In what follows, I will show why both of these definitions are equivalent, namely, if A and B have the same remainder r by the division by n, then n divides A minus B here, and if n divides A minus B, then A and B must have the same remainder modulo n. To prove the first claim, we write A as n times a certain integer k plus the remainder r, B as n times another integer k prime plus the same remainder r, and from here we see that A minus B is equal to nk plus r minus nk prime minus r, from which we can cancel both of the r's, and we get n times k minus k prime, which means that A minus B is divisible by n. Hence the first claim. To prove the second claim, we write A as n times k plus a remainder r, and B as n times k prime plus r prime, from which we deduce that A minus B is equal to n times k minus k prime plus r minus r prime. This implies actually that r minus r prime is equal to A minus B all minus n times k minus k prime, from which we deduce that if n divides A minus B, then n must divide r minus r prime because n divides n times k minus k prime. Now let me remind you that we would like to prove that r is equal to r prime, which means that r minus r prime is equal to 0. And to do this, and without loss of generality, one can suppose that r prime is lesser than r, which implies that r minus r prime is greater than 0, but it is also actually strictly lesser than n, and this second inequality here follows from the fact that actually r and r prime are both lesser strictly than n, so one can place r prime here and r here, from which we see that their difference, which is the distance between r prime and r, is strictly lesser than n. This fact implies that r minus r prime can only be 0 because r minus r prime is a multiple of n strictly lesser than n, and the only multiple of n strictly lesser than n is actually 0. So r minus r prime is equal to 0, which implies that r is equal to r prime. Let us now get back to our claims and prove that if A is congruent to B modulo n, and c is congruent to d modulo n, then a plus c is congruent to b plus d modulo n, and a times c is also congruent to b times d modulo n. And this is our second claim. Proving that a plus c is congruent to b plus d modulo n is the same thing as proving that a plus c minus b plus d is divisible by n. This is actually a trivial fact because we can rewrite this as a minus b plus c minus d, but since a is congruent to b modulo n, we know that this is a multiple of n, so this number belongs to the multiple of n, which we denote nz, and we also know that c is congruent to d, which is equivalent to c minus d is a multiple of n, which means that this is also a multiple of n, and the sum of two multiples of n is a multiple of n. Hence our claim. Proving our second claim is a little bit trickier. Let me remind you that proving that AC is congruent to BD modulo of n is equivalent to showing that AC minus BD is a multiple of n. Now to get to my goal, I would like to transform this expression to use the fact that n divides A minus B and n divides C minus D. So I should make both of them appear in this algebraic identity. To do this, I write that this is equal actually to A times C minus D. So I add it to AC minus AD, and to cancel this, I will have to add AD again, from which I subtract BD. Surprisingly, actually, this is equal to A times C minus D plus D times A minus B. But we know that this is a multiple of n, and this too is a multiple of n, which means that AC minus BD is a combination of two multiples of n, and thus it is also a multiple of n. And this ends our proof, from which we know that addition and multiplication are well defined on a clock. Notice now that if I apply this claim here to A congruent to B modulo n and A congruent to B modulo n again, then one gets that A times A is congruent to B times B modulo n, which we can write that A squared is congruent to B squared modulo n. And from this one and this one here in our second claim, one can deduce that A squared times A is congruent to B squared times B modulo n, and this is equivalent to A cubed is congruent to B cubed modulo n. Actually, in the same fashion, one can prove if A is congruent to B modulo n, then we have that A to the m is congruent to B to the m modulo n, where m is any positive integer. There is an important thing to understand here. Congruences behave like equalities in the real world. We can indeed add numbers modulo n in the same fashion as numbers in the real world. We can also do multiplications and do pairing to a certain integral power. However, we will see that multiplication is a little bit trickier than addition. Before we move on and see how to apply addition and multiplication to real number theoretical problems, let us see what it means to subtract 2 hours on a clock. In other terms, what does A minus B modulo n mean? This actually should be the same thing as A plus minus B modulo n, but then what does minus B mean? Minus B should mean going backward of the number B on a clock of n hours, starting of course from 0. So if you take this clock that you see here, it is a 4 hours clock, and going backward by 3 means that we're gonna turn to the left from 0 by 3 hours, and we will be here in 1 hour. So minus 3 is the same thing actually as 1 modulo 4, and notice actually that this is the same thing as 4 minus 3 modulo 4. So algebraically, to define minus b, actually minus b should be the number that you add to b to get 0 modulo n, and if b actually is a number between 0 and strictly lesser than n, then minus b is the same thing as n minus b modulo n. Notice that n minus b will be a positive number, and this is because if we add n minus b to b, one gets 0 modulo n, which means that n minus b should be the number minus b. So if you try this on a concrete example, minus 3 is the number that I add to 3 to get to 0, and the number that I add to 3 to get to 0 is 1, which means that minus 3 is actually 1, modulo 4 of course. Let us now move on and see how this is applied to real number theoretical problems. And in our first example, we would like to know whether 6 powers 2021 minus 1 is a multiple of 5 or a multiple of 7. Actually, we cannot do straight computations because this number is very big, and in order to answer our question, we will use congruences and their properties. Indeed, we know from congruences that 6 is congruent to 1 modulo 5, and we know from the properties of congruences that 6 to the 20,021 is also congruent to 1 to the 20,021 modulo 5, which implies that 6 to the 2021 is congruent to 1 modulo 5 because 1 to the 2021 is equal to 1, and this means that 6 powers 2021 minus 1 is congruent to 0 modulo 5, which implies that 5 divides this number here. Awesome. Let us now see whether this is true for 7 too. We know that 6 is congruent to minus 1 modulo 7, from which we deduce that 6 powers 2021 is congruent to minus 1 powers 2021 modulo 7, and we know that minus 1 powers 2021 is the same thing as minus 1, so 6 powers 2021 is congruent to minus 1 modulo 7, and minus 1 modulo 7 actually is 6 modulo 7, so we deduce that 6 powers 2021 is congruent to 6 modulo 7, which means that 6 powers 2021 minus 1 is congruent to 6 minus 1, which is 5 modulo 7, and this means that the remainder of the division of this number here by 7 is equal to 5, which also means that 7 does not divide 6 powers 2021 minus 1. Whoa, congruences are actually a very powerful tool. In our second example, we would like to find the remainder of the division of 12 factorial by 13. Let me remind you that 12 factorial is 12 times 11 times 10 times 9 until we get to 1. A straight computation yields actually that 12 factorial is equal to 479,000,016. Now, as you can see, this is a huge number to which we can apply division with remainder to get that 12 factorial actually is equal to 36,846,276 times 13 plus 12. So the remainder of the division of this number by 13 is actually equal to 12. Now imagine that we do not have a calculator and we would like to use congruences to find the same result. Indeed, we can write 12 factorials as 12 factorial is congruent to 12 times 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 modulo 13. But to simplify this, we can use some properties of congruences because we know actually that 12 modulo 13 is the same thing as minus 1 modulo 13. So we will write that 12 is minus 1 times 11, which is minus 2, 10 is minus 3, 9 is minus 4, 8 is minus 5, 7 is minus 6, and all of this times 6 times 5 times 4 times 3 times 2 times 1, of course, but it is useless, modulo 13. And from here, if you compute this number here, we find that it is equal to 24, so this is congruent to 24 times this 24 here, so this is 24 times 24 times 25, all times 36 modulo 13. 25 is actually 5 times 5, and 36 is 6 times 6, of course. But we know that modulo 13, 24, is actually the same thing as 11. The second 24 is also congruent to 11 modulo 13, 25 is the same thing as 12 modulo 13, and 36 is 10 modulo 13. So all of this is congruent to this number modulo 13, and actually let me remind you that we're capable of doing this thanks to the properties of congruences about addition and multiplication. Now 11 is actually the same thing modulo 13 as minus 2. This 11 here is also a minus 2. 12 is congruent to minus 1, and 10 is congruent to minus 3 modulo 13. Now if you do this multiplication here, we find that this is actually congruent to 12 modulo 13, which means that the remainder of the division of 12 factorials by 13 is equal to 12, and we've done this without doing any sophisticated computation. Whoa. In this example, we would like to compute the remainder of the division of 2 powers 2021 by 11, and to do so, let us compute small powers of 2 modulo 11. First, we know that 2 squared is congruent to 4 modulo 11, 2 cubed is congruent to 8 modulo 11, 2 to the 4th is congruent to 16 modulo 11, but 16 modulo 11 is the same thing as 5 modulo 11, so this is not very helpful for our computations. We go further to find that that 2 powers 5 is actually the same thing as 2 powers 4 times 2 modulo 11. We know that 2 powers 4 is the same thing as 5, so this is equal or congruent, if you'd like, to 5 times 2 modulo 11, which is 10 modulo 11. So this is still not very helpful, but we can see that 10 modulo 11 is congruent to minus 1 modulo 11, which can be helpful for our computations. Now 2 power 6 is congruent to 2 to the 5th times 2 modulo 11. 2 to the 5th is congruent to minus 1, so this is congruent to minus 2 modulo 11, which is still not very helpful. We go further to compute 2 power 7, which is congruent to 2 to the 6th times 2 modulo 11. 2 to the 6th is minus 2, so this is congruent to minus 4 modulo 11, and minus 4 modulo 11 is the same thing as 7 modulo 11, which is still not very helpful to compute powers. We go further here and compute 2 powers 8, which is the same thing as 2 powers 7 times 2 modulo 11 still, and this is congruent to minus 4 times 2 modulo 11, which is congruent to minus 8 modulo 11, and minus 8 is the same thing as 3 modulo 11. Actually here I am looking for the smallest power of 2 that gives 1 modulo 11, which will help us find the remainder of 2 powers 2021 modulo 11, and you will see how. Now 2 powers 9 is congruent to 2 powers 8 times 2 modulo 11, and this is congruent to 3 times 2 modulo 11 because 2 powers 8 is congruent to 3, so we found that this is equal to 6 modulo 11, and surprise, actually 2 to the 10th is congruent to 2 to the 9th times 2 modulo 11. 2 to the 9th is 6, so 6 times 2 is 12, so this is congruent to 12 modulo 11, which is congruent to 1 modulo 11. Bingo. Actually, notice that we could have deduced this from here because 2 to the 5th is congruent to minus 1 modulo 11, and if we square both of the sides, one gets that 2 to the 5th all powers 2 is congruent to minus 1 powers 2, which is 1 modulo 11, and we know that 2 to the 5th powers 2 is actually 2 to the 10th. Now if I write things down again, we would like to find the remainder of the division of 2 powers 2021 by 11, and we know that 2 powers 10 is congruent to 1 modulo 11, but we know that 2021 is actually equal to 202 times 10 plus 1. Now if you power both sides here by 202, one gets that 2 to the 10th, all powers 202, is congruent to 1 powers 202, which is the same thing as 1 modulo 11, and from here we deduce that 2 powers 10 times 202 is congruent to 1 modulo 11, and now if you multiply both sides by 2, one gets that 2 powers 10 times 202 plus 1 is congruent to 2 modulo 11, and from here we deduce that 2 powers 2021 is congruent to 2 modulo 11, and this holds because 2021 is equal to 202 times 10 plus 1, from which we get the desired result, namely 2 powers 2021 has remainder 2 by division by 11. Powerful congruences, right? Part 2 ends here, and we will inspect in Part 3 more applications of congruences. Thank you for listening.